650 light-years away, a star the size of our entire inner solar system is behaving in ways that have alarmed astronomers for years. It dims without warning. It flares. It pulses on a rhythm nobody could explain. That star is Betelgeuse, and confirmed data now changes everything we thought we knew. A hidden companion, a gas wake cutting through space. Decades of mystery suddenly snapping into focus. One question nobody can fully dismiss: how close is this star to the end? If this grips you, hit like and subscribe. Take a breath. We launch into the deep. Betelgeuse is the one star in our sky that astronomers genuinely watch with urgency. Not because it is the largest, not because it is the brightest, but because it is doing something no other star this close to us has ever done in recorded human history. It is changing, visibly, measurably, in ways that do not follow the rules. Most stars are locked points of light, fixed, predictable. You could study them for a lifetime and see nothing move. Betelgeuse breaks that entirely. It sits in the shoulder of the constellation Orion, glowing a deep reddish orange that stands out even to the naked eye. That colour is not just beautiful, it is a warning. Red supergiants burn at lower temperatures than younger stars because they have already consumed most of their fuel. They are in the late stages of a journey that ends in catastrophe. Betelgeuse sits roughly 650 light-years from Earth. In everyday terms, that sounds enormous. In cosmic terms, it is practically next door, close enough that the surface of the star is not just a pinpoint of light, it is a resolvable disk. Astronomers can actually map features on it. They can track storms, measure convection cells, and watch the atmosphere move in real time. That proximity is what makes Betelgeuse so valuable and so alarming. Because, for the past several years, the data coming back from it has been strange. Not slightly off, genuinely unexplained. The star has been dimming and brightening on two separate cycles, one short, one long, and neither one matched the existing models cleanly. Teams around the world pointed their best equipment at it and came back with data that raised more questions than it answered. Here is what is confirmed. Betelgeuse is a variable star. Its brightness shifts are real and documented across more than a century of observations. That much is not in dispute. Here is what was a mystery until very recently. Why the long cycle exists at all, and what was driving the dramatic swings that went beyond anything the star's own internal physics could explain. The answer, when it finally arrived, came from a direction almost nobody expected. Something had been hiding inside the system, orbiting so close to Betelgeuse, buried so deep in its glare that every telescope pointed at it had missed it for decades. A companion. A whole second star. And the moment scientists confirmed it was real, every strange data point from the past 10 years suddenly snapped into focus. But before we get to the companion, you need to understand what Betelgeuse actually is. Because the size of this star is the kind of thing that changes how you think about space. And that is the next stop. But understanding the scale is only the beginning. Because once you know how big Betelgeuse is, the behavior it has been showing takes on a completely different weight. A star that large does not flicker casually. When something that size changes, it changes for a reason. If you replaced our own star with Betelgeuse, every inner planet would be gone. Mercury, Venus, Earth, Mars, all of them swallowed. The surface of Betelgeuse would stretch out past the orbit of Mars and keep going. In some estimates, it would reach nearly to Jupiter. The star is so large that if you placed a model of it at one end of a football field, our own star would be the size of a marble at the other end. Numbers like that stop feeling real after a while. So let us try a different approach. Light, the fastest thing in the universe, takes about 8 minutes to travel from our star to Earth. If you fired a beam of light from one side of Betelgeuse to the other, it would take roughly 7 hours to cross. That is a journey of over 6 billion miles just to get from one edge to the other. This is confirmed, not an estimate. Astronomers have measured Betelgeuse's angular diameter directly using interferometry, a technique that combines signals from multiple telescopes to produce far more precise measurements than any single instrument could manage. The result has been refined multiple times, and while the exact number shifts slightly depending on how you define the outer boundary of the star, the scale is not in question. Betelgeuse is between 700 and 900 times the width of our own star. Here is what that scale means for everything else we are about to discuss. When Betelgeuse moves, it moves slowly. When it sheds gas in quantities that would blanket entire solar systems. When something orbits inside its atmosphere, that something is not skimming past a surface. It is ploughing through a vast ocean of stellar material that extends millions of miles into space, beyond what we would normally call the star's edge. That outer atmosphere is called the extended atmosphere or the outer chromosphere. It is not empty. It is filled with gas and dust being slowly pushed outward by the radiation and convection activity happening deep inside the star, and it is enormous in its own right. This matters because of what we eventually found inside it. A companion star, orbiting at a distance that, in our own solar system, would put it roughly between our star and the planet Jupiter, close enough to be inside Betelgeuse's extended outer atmosphere, close enough that every orbit it completes, it is physically cutting through a cloud of stellar material the size of a small solar system, and the wake that creates is exactly what finally gave it away. But to understand why that wake matters, you first need to understand what was being measured before anyone knew the companion existed, because the data was strange long before anyone had an explanation for it. What comes next is where the mystery really starts. And to understand it fully, you need to know what was being measured before anyone had the right explanation. Variable stars are not unusual. Plenty of stars in our galaxy pulse, dim, and brighten on regular cycles. It is part of normal stellar physics. Betelgeuse is a variable star, and that has been known for over a century. What made Betelgeuse different was not the variation itself, it was the shape of it. Most variable stars follow clean, predictable rhythms. You can set a timer by them. Their brightness rises and falls like a wave, and the wave is consistent. Betelgeuse does something messier. It runs on 2 overlapping cycles at the same time, and the 2 cycles interfere with each other in ways that make the star's behavior look almost erratic if you do not know what you are looking for. The first cycle is roughly 400 days long. This one is understood. It is caused by pulsations, physical oscillations inside the star itself, where layers of gas contract and expand in a repeating rhythm. It is like a heartbeat, imperfect, slightly uneven, but consistent enough to track across decades. Astronomers call this kind of variation semi-regular, and for Betelgeuse, the 400-day pulse has been tracked and mapped for decades. The second cycle is far longer, roughly 2,100 days, which works out to close to 6 years, and this one did not fit. It is called the long secondary period. That name sounds technical, but what it means is simple. There is a second, slower wave of brightness change sitting underneath the faster one, and for years, nobody could figure out what was causing it. Here is why that matters. The 400-day pulse makes sense if you look at the star's own interior. You can model it, predict it, explain it with the known physics of stellar oscillation. The 6-year cycle did not respond to those models cleanly. Internal pulsations could not account for something that slow and that large. The math did not work. Theories multiplied. Giant convection cells on the surface, which are confirmed to exist and are enormous, were one candidate. Magnetic activity was another. A rotating asymmetry in the star, some kind of lopsided shape slowly spinning into and out of view, was floated as a possibility. none of them held up completely. And then came the dimming event of 2019, the one that turned casual interest into something closer to alarm. In the second half of 2019, Betelgeuse began to fade. Not gradually, the way a slow cycle would predict. Sharply, within a few months, it had dropped to a brightness level that placed it outside the historical range. By early 2020, it was so faint it had fallen out of the 50 brightest stars in the night sky, a list it had held a place on for as long as humans had been watching. Astronomers did not have an explanation ready, and that gap between the data and the models is exactly where the real story begins, because what came next would change how we read everything. By January of 2020, Betelgeuse had faded to roughly 40% of its normal brightness. For a star that is visible to the naked eye, that is not a small change. The difference was obvious. Amateur astronomers noticed it. Casual observers noticed it. The scientific community was already watching closely. And now everyone else was watching too. The first question was straightforward. Had this happened before? The answer was yes, but not like this. Historical records showed that Betelgeuse had experienced dimming episodes over the past century, tied to the normal rhythms of its two overlapping cycles. But the 2019 event was deeper and faster than the models predicted. The timing did not align cleanly with either the 400-day pulse or the 6-year secondary period. Two leading explanations emerged almost immediately. Both were serious. Both had evidence behind them. The first was internal. Some researchers proposed that Betelgeuse had experienced a convective outburst, a massive eruption of hot gas rising from deep inside the star and punching through the outer layers. When superhot gas from the interior breaks through the surface, it does not brighten the star cleanly. As it rises and expands outward into cooler space, it can actually cool and dim the visible surface beneath it because the erupted material blocks light from escaping. Convective outbursts are confirmed physics. Betelgeuse is known to have convection cells on its surface that are confirmed to be comparable in size to Earth's entire orbit. A large convective event was physically plausible. The second explanation was external. A sudden ejection of material from the star's surface, cooling rapidly as it moved away, could form a dust cloud that sat between the star and Earth. Dust absorbs starlight. Enough dust in the right position would produce exactly the kind of dimming that was being observed. Both theories had merit. Both were actively investigated. Here is what the data eventually confirmed. It was the second one. A surface mass ejection, now called the Great Dimming Event, released an enormous amount of material from the star's outer layers. That material cooled into dust. The dust formed a partial screen. And from Earth, 650 light-years away, Betelgeuse went dark. This was a new category of stellar behavior. Scientists had observed smaller mass ejections before, but the scale of what Betelgeuse produced in late 2019 was roughly 400 billion times larger than anything previously recorded from this star. That number is worth sitting with for a moment. The dust eventually dispersed. By mid-2020, Betelgeuse had returned to normal brightness and then exceeded it, brightening past its historical average and staying elevated, which raised an entirely new question. Why did it come back brighter? And what was driving the 6-year cycle that kept humming along underneath everything else, completely unaffected by the dramatic surface event? The answers were connected, and they pointed towards something nobody had directly seen yet. After the Great Dimming ended, something unexpected happened. Betelgeuse got bright, not just back to normal, noticeably brighter than its historical average. By 2023, it had climbed to levels that put it among the most luminous objects in Orion's belt region by naked eye comparison, outshining predictions that had been stable for decades. This is confirmed observational data. Multiple independent photometric surveys recorded it. The star had gone from its lowest measured point in modern history to one of its brightest within roughly 3 years. That swing is not what healthy, stable stars do. And underneath this brightness surge, the 6-year cycle was still running, steady, rhythmic, completely indifferent to the drama of the surface ejection. Whatever was driving that long period, it was not connected to the dust cloud event. It was something structural, something orbital. The long secondary period, that roughly 2,100-day rhythm, had been a puzzle for so long that astronomers had a name for the category of stars that show it. They are called long secondary period variables. And Betelgeuse is one of the most studied examples in the sky, which made the fact that the cause remained unknown especially frustrating. Here is what made it particularly strange. The 6-year cycle showed up not just in brightness measurements but in spectroscopic data, meaning the actual light spectrum of the star was shifting on that same schedule. Spectroscopy measures the chemical fingerprints in starlight, and changes in the spectrum can reveal things like gas motion, temperature shifts, and the velocity of material moving toward or away from Earth. The spectrum of Betelgeuse was changing every 6 years in a pattern that suggested material was being disturbed in the outer atmosphere on a regular, repeating basis. Not chaotically, not randomly, periodically. That kind of periodicity has one very natural explanation in astronomy. Something was orbiting. A companion star moving through the outer atmosphere of Betelgeuse would do exactly this. Every time it completed one orbit, it would stir the surrounding gas, creating a moving disturbance in the spectrum, a shift in the dust distribution, and a modulation of the total light reaching Earth. The theory had been floated before. Multiple papers had suggested a companion as the best explanation for the long secondary period, but direct evidence was elusive. Betelgeuse is so bright and so large that anything orbiting close to it would be completely drowned out by its glare. Finding a companion would require either extraordinary instrumentation or a very specific observing window. In December of 2024, astronomers got both. The Gemini North Telescope in Hawaii, equipped with a specialized high-contrast imaging instrument, captured something in the immediate vicinity of Betelgeuse that should not have been there if the star were alone. A point of light. Faint. Close. Exactly where the orbital models predicted a companion would be. The companion was real, and what it turned out to be surprised almost everyone. The night Betelgeuse startled the entire sky watching community was not a supernova, it was a dimming, a fade, a star that billions of people had looked up at their whole lives quietly stepping back into the dark. In September of 2019, standard photometric monitoring showed that Betelgeuse had begun dropping below its historical brightness baseline. At first, the decline fit within the expected range of its normal variation. Variable stars dip, that is what they do. The early numbers did not set off immediate alarms. By November, the drop was steep enough to draw wider attention. By December, it had crossed into territory that placed it statistically outside the normal range. And by January and February of 2020, Betelgeuse had reached a brightness level not recorded in the modern era of precise astronomical measurement. The response from the scientific community was rapid and coordinated. Observatories around the world pointed instruments at Orion. Spectroscopic data, photometric data, infrared data, ultraviolet data from orbiting telescopes, including the Hubble Space Telescope, all of it began flowing in. The star was being watched from every angle, across every wavelength scientists could access. And what they found in that data was genuinely confusing. The dimming was not uniform across wavelengths. Infrared observations showed that Betelgeuse had not actually lost heat output in proportion to its visible dimming. This was a critical clue. If the star itself had cooled or contracted, the drop should appear consistently across the spectrum. Instead, visible light was suppressed, while longer wavelength infrared signals remained comparatively strong. That asymmetry pointed toward an external cause, something between the star and the telescope, something that was absorbing and scattering, shorter wavelengths of light more than longer ones. Dust does exactly that. The infrared data also showed an increase in thermal emission from material surrounding the star. Cool dust radiates in infrared, and there was more of it around Betelgeuse in early 2020 than there had been before. Here is what was confirmed in peer-reviewed research published after the event. A surface mass ejection from Betelgeuse sometime in late 2019 released an enormous cloud of stellar material. Moving away from the star, the material cooled and condensed into dust particles. That dust cloud drifted into the line of sight between Betelgeuse and Earth, blocking a portion of the visible starlight and creating the observed dimming. The ejection itself, the physical release of material from the stellar surface, was caused by a massive convective cell erupting through the outer layers of the star. So both of the early hypotheses had a piece of the truth. It was a convective event that caused the ejection that caused the dust. The star was not dying faster than expected. It was not a precursor to a supernova. It was a dramatic, unprecedented surface event on an already dramatic, unprecedented star. But it left something behind. A gap in the models. A question still unanswered. Why did the 6-year cycle keep running through all of it, untouched, as if the dust cloud had never happened at all? That question had a stranger answer than anyone was prepared for. When astronomers talk about the Great Dimming, they are careful with their words. In science, words like catastrophic or alarming carry weight. Using them in the wrong context damages credibility. So, in the months following the 2019 to 2020 event, most researchers were measured and deliberate. They described what they observed. They offered hypotheses. They waited for data. But inside those measured words was a genuine undercurrent of concern. Here is why. Betelgeuse is a red supergiant at an advanced stage of stellar evolution. That is confirmed. It has exhausted its hydrogen fuel and is now burning heavier elements in its core. That process has a known endpoint, a core collapse supernova. The star will, at some point, run out of fuel entirely, and when it does, the core will collapse in a fraction of a second, triggering an explosion powerful enough to briefly outshine entire galaxies. The question has never been if, it has always been when. Before the Great Dimming, the best estimates placed the supernova anywhere from 100,000 to a few 100,000 years in the future. That sounds like forever. In human terms, it is. But in stellar terms, it is an eye blink, and some of the observational data coming out of Betelgeuse in the years before 2019 had quietly started trimming those estimates. A 2023 study from Japanese researchers analyzing surface pulsation data and comparing it to theoretical models of late-stage stellar evolution proposed that Betelgeuse might be closer to the end of its carbon-burning phase than previously thought. If carbon burning was nearly complete, the remaining fuel cycles would be far shorter. The star could, in theory, approach a supernova on a timescale of decades rather than millennia. That paper was not a fringe claim. It was peer-reviewed and widely discussed. It did not say the explosion was imminent. It said the timeline was worth revising. And then the Great Dimming happened, and people started asking the obvious question: was this a sign? Here is the honest answer. At the time, unknown. Surface mass ejections are not confirmed precursors to a supernova. They happen on stars that are not near death. The dust cloud explanation, once confirmed, actually argued against imminent collapse because it was a surface event, not a core event. Deep inside Betelgeuse, the fusion processes driving the eventual explosion were not directly visible. But the uncertainty was real, the data was real, and the 6-year cycle kept cycling, untouched, suggesting something structural in the system that the dust cloud story did not explain. Some researchers began revisiting the companion hypothesis with more urgency. If something was orbiting Betelgeuse on a 6-year period, It could be responsible for both the long secondary period variation and, potentially, some of the surface disruption. Nobody had proof yet. What came next would change that entirely. And the instrument that found the answer was pointed at the sky from the top of a volcano in Hawaii. The instrument that finally caught Siwaha is called Alopeke. That name comes from the Greek word for fox. It is a high-contrast speckle imaging system mounted on the Gemini North Telescope on the summit of Mauna Kea in Hawaii, at an altitude of nearly 14,000 feet. At that elevation, above most of the atmospheric distortion that blurs ground-based astronomy, Alopeke is designed to separate closely spaced objects that would blend into a single, unresolvable blob at lower altitude. Speckle imaging works by taking thousands of very short exposures in rapid succession. Each individual frame captures a slightly different distortion pattern from the atmosphere. By combining and analyzing those frames mathematically, astronomers can reconstruct an image sharper than any single long exposure could produce. The technique is specifically designed for exactly the problem posed by Betelgeuse, a brilliant star with a potentially faint companion hiding in its glare. On December 9th of 2024, a team led by Steve Howell of the Ames Research Center pointed Alopeke at Betelgeuse. What they found was a point source, separate from Betelgeuse, distinct, located at a distance from the main star that corresponded to roughly 4 astronomical units, which is approximately the same distance as the gap between our star and the asteroid belt, compressed into the glare of a supergiant. The companion was real. The findings were published in the July 2025 issue of the Astrophysical Journal Letters. The paper was titled "The Probable Direct Imaging Detection of the Stellar Companion to Betelgeuse." The word probable in the title reflects the standard of scientific caution, not doubt. The detection was clear. The team was confident. Further observations would follow. Initial analysis of the companion's properties suggested it was a low-mass star, somewhere around 1.4 to 1.7 times the mass of our own star. At that mass, the companion would be a main sequence star, meaning it is still actively fusing hydrogen in its core, still relatively young in stellar terms, still burning steadily. This was unexpected. The leading theoretical models before the detection had suggested the companion, if it existed, was more likely a compact object, a white dwarf or a neutron star, a dead stellar remnant orbiting silently within the system. Finding a living, active star instead forced a rethink of the system's history and the forces shaping Betelgeuse's behavior. The companion was given a name, Siwaha, from the Arabic word for bracelet, a nod to the Arabic roots of Betelgeuse's own name, which translates roughly as the hand of the giant, a bracelet around the hand of the giant. The naming carried a quiet elegance, but the name was the easy part. What came next was understanding what Siwaha was actually doing to the star it orbited, because the wake that the Space Telescope detected just months later answered questions that had been building for a decade, and it was stranger and more beautiful than the models had predicted. Siwaha does not orbit outside Betelgeuse the way a planet orbits a star. It orbits through it. At 4 astronomical units out, Siwaha is physically inside the extended outer atmosphere of Betelgeuse. The star's outer chromosphere and the layers of gas being continuously shed from its surface extend far beyond what we would normally draw as the star's edge. They reach outward for many times the star's visible radius, and Siwaha, at its orbital distance, is embedded in that material, surrounded by it, ploughing through it at orbital speeds with every pass. Think of a boat moving through water. The hull of the boat does not just touch the water in front of it, it compresses it, pushes it aside, and leaves a churning trail behind it, a wake that persists for some time after the boat has passed. The shape of that wake tells you something about the boat's size, speed, and direction, even if you cannot see the boat directly. Siwaha does exactly this. but on a scale that covers millions of miles. As Siwaha moves through the outer atmosphere of Betelgeuse, it compresses the surrounding gas ahead of it and drags a dense, expanding trail of disturbed material in its path. This wake is not a thin line. It is a broad, turbulent structure that expands outward and persists for months. The gas in it is denser than the surrounding atmosphere, which means it absorbs and scatters light differently. And since the whole system is rotating relative to Earth, different parts of this wake move in and out of our line of sight on a predictable schedule. This is the confirmed mechanism now, published in a paper accepted by the Astrophysical Journal in early 2026, led by Andrea Dupree of the Harvard and Smithsonian Center for Astrophysics. The team analyzed nearly 8 years of spectroscopic data from the Hubble Space Telescope and multiple ground-based observatories and tracked the changing light signature of Betelgeuse across each 6-year orbital cycle. The signature of the wake appeared consistently. Every time Siwarha crossed in front of Betelgeuse from Earth's perspective, the spectrum shifted. Gas velocities changed. Certain chemical signatures brightened or dimmed in ways that matched a dense region of material passing through the line of sight. The pattern repeated. The timing matched the orbital period. This is not a theory anymore. It is a confirmed detection of the companion's influence on the atmosphere around it, and what it means for every previous mystery is significant. The 6-year brightness cycle, the one that defied explanation for decades, is now explained. The spectroscopic shifts that puzzled researchers are explained. The unusual brightness surges and dips that sat on top of the 400-day internal pulse are explained. All of it traces back to one small star cutting through the outer layers of a giant, leaving a wake that ripples across the light we see from 650 light-years away. The system is not a single, isolated dying star. It is a binary. And that changes the picture entirely. But Siwaha's wake does more than explain the past. It is also showing us something about the future. And that part is what the next chapter is about. Knowing Siwaha exists changes the timeline question in a way that matters. Before the companion was confirmed, the 6-year cycle had no clean physical explanation. That gap left room for speculation, including the more alarming kinds. Some interpretations of the data pointed toward accelerating instability in Betelgeuse's core. Others tied the unusual brightness swings to deep evolutionary changes that could shorten the supernova timeline. Now those interpretations have to be reassessed, because the 6-year cycle was not a sign of internal collapse. It was an orbital signal from a companion star doing exactly what a companion star at that distance would do. Here is what that means, stated clearly. The behavior of Betelgeuse, that most strongly suggested it might be approaching a dramatic end faster than expected, was caused by something external to Betelgeuse's own evolution. The star's core is not necessarily accelerating toward collapse on the short timescales some earlier papers proposed. This does not mean Betelgeuse is stable forever. It is not. It is a massive red supergiant, and it will explode. That is not in dispute. The question of when remains genuinely open, and the honest answer, based on current data, is that it will most likely be somewhere between 100,000 and a few 100,000 years from now. Some researchers, accounting for the new binary system context, now lean toward the longer end of that range. Others hold that the internal evolution data still supports a shorter window. The companion discovery does not definitively settle the timing question. It removes one major source of false urgency while leaving the genuine underlying uncertainty intact. What the discovery does change is how we model the system. Betelgeuse and Siwaha formed together, probably around 10 million years ago, from the same cloud of gas and dust. They have been orbiting each other ever since. During that time, Betelgeuse expanded from a normal star into the giant it is today, and Siwaha has been orbiting steadily while its companion swelled to nearly engulf it. Siwaha's orbit is gradually decaying. As it moves through the dense outer atmosphere of Betelgeuse with every pass, it loses a small amount of energy to drag. Over time, this will cause Siwaha to spiral slightly inward. The process is slow, measured in tens of thousands of years, but it is happening. What happens when Betelgeuse eventually does explode is a separate and genuinely interesting question. A supernova in a binary system does not simply destroy one member. The shockwave, the radiation burst, and the dramatic mass loss can unbind the orbit entirely, flinging the surviving star outward at high velocity. Siwaha could one day become a runaway star, ejected from the system at speeds of tens of miles per second, but that is far in the future. Right now, Siwaha is on the far side of Betelgeuse from Earth's perspective, hidden behind it, and it will stay hidden until roughly 2027, when orbital geometry brings it back into a viewable position. Astronomers are already planning for that window. What they observe when Siwaha re-emerges could refine everything we currently know about this system. And Chapter 11 is where we look at why that observation matters more than almost anything else in stellar astronomy right now. Siwaha is currently invisible to us, not because it has disappeared, because of geometry. The orbital path of Siwaha carries it behind Betelgeuse from Earth's perspective, placing it in a position where the supergiant itself blocks our view. Based on orbital calculations using the confirmed period of roughly 2,100 days, Siwaha is expected to emerge from behind Betelgeuse and become observable again around 2027. That window is being treated as one of the most significant near-term observational opportunities in stellar astronomy. Here is why it matters so much. The first confirmed detection of Siwaha in December 2024 gave astronomers a position and an estimated brightness. The subsequent observations from the Hubble Space Telescope confirmed the wake and provided spectroscopic data about Siwaha's influence on the surrounding gas. But what has not yet been achieved is a clean, detailed, direct observation of Siwaha itself during a period when it is fully separated from Betelgeuse in the line of sight. When Siwaha re-emerges in 2027, instruments will be ready. Multiple telescope teams have already indicated plans to target the system during that window. The goal is to gather precise photometric and spectroscopic data on Siwaha directly, not just through its effect on the surrounding material. What researchers hope to nail down includes the companion's exact mass, its temperature, its luminosity, and whether it shows any signs of interaction, effects from its repeated passages through Betelgeuse's outer atmosphere. A star that has been orbiting inside a red supergiant's outer layers for millions of years may carry signatures of that exposure in its own spectrum. Absorbed material, altered surface chemistry, possibly even a surrounding shroud of Betelgeuse's ejected gas. This is not confirmed yet. It is a genuine scientific unknown and a compelling one. There is also a broader significance that extends beyond this single system. Betelgeuse is one of the closest and most observable red supergiants in the galaxy. Studying how its binary companion shapes its atmosphere, drives its mass loss, and modulates its brightness gives astronomers a template. The universe is full of red supergiants, too distant and too faint to study in this kind of detail. Whatever we learn from Betelgeuse and Siwaha becomes a reference point for interpreting those distant, dimmer systems we can barely resolve. In a real sense, understanding Betelgeuse means understanding a category of stars that spans a significant portion of the most massive objects in the galaxy. Stars that end in supernovae. Stars that seed the universe with heavy elements when they explode. Stars that are, in the deepest sense, the factories that produce the material from which planets and life eventually form. Siwaha's wake is not just a quirky feature of a nearby star. It is a window into how giant stars die. And what happens inside Betelgeuse in the decades and centuries ahead will eventually tell us something that no model alone can fully predict. The surface of Betelgeuse itself is the next place to look. Because what is happening there right now is something that no other star lets us watch this closely. The surface of Betelgeuse is not a smooth, glowing sphere. It is a churning, heaving landscape of gas in constant violent motion. Enormous columns of superheated material rise from deep inside the star, punch through the visible surface, spread outward, cool, and sink back down, only to be replaced by new columns rising behind them. The process never stops. It has been running for millions of years, and it will keep running until the core finally gives out. This process is called convection, and every star with a convective outer layer does some version of it. On our own star, convection cells are small enough that their tops, called granules, measure roughly 600 miles across. They tile the visible surface in a shifting mosaic of bright centers and dark edges. They are beautiful and they are tiny. On Betelgeuse, convection cells are confirmed to be orders of magnitude larger. Observations from multiple interferometric imaging campaigns, including work done with the Atacama Large Millimeter Array and the Very Large Telescope in Chile, have resolved individual bright and dark regions on Betelgeuse's surface that span distances comparable to the distance between Earth and our star. That is roughly 93 million miles. For a single convection cell, one bright spot on the surface of Betelgeuse could swallow everything inside Earth's orbit and still have room left over. These cells move slowly by human standards, but rapidly by stellar standards. A single convective cycle, from the rise of a hot column to its eventual collapse and replacement, takes months to years. The surface of Betelgeuse is never the same shape twice. It bulges outward in places where hot columns are rising, flattens or dips where cooler material is sinking, and shifts asymmetrically over timescales that are visible in the data across a few years of observation. This asymmetry is part of why Betelgeuse's brightness varies even on the shorter 400-day cycle. As different proportions of the surface are dominated by hot, bright rising cells versus cooler, dimmer sinking regions, the total light output shifts. The star is literally uneven in its glow, and that unevenness rotates slowly through our line of sight. The surface activity also drives the mass loss that makes Betelgeuse such a powerful source of material for the surrounding space. When a massive convective cell erupts through the surface with enough force, it can throw material upward fast enough to escape the star's gravity entirely. Over millions of years, this steady stream of lost material has built up a large, complex circumstellar envelope surrounding the entire system. That envelope is now also being shaped by Siwaha. The companion's orbital motion stirs and compresses parts of the surrounding material, creating asymmetries in the envelope that observers can detect. But the surface itself, that boiling, shifting, asymmetric expanse, is only the outer layer of a far more complex interior. And what is happening in the deeper layers of Betelgeuse right now is where the real countdown lives. The next chapter goes inside. Below the churning surface of Betelgeuse, something fundamental is burning out. To understand what is happening inside this star right now, start with how stars work in general. A star is a balance between two forces pulling in opposite directions. Gravity wants to collapse the star inward. The energy produced by nuclear fusion in the core pushes outward. As long as fusion keeps running, the star holds its shape. When a star the size of Betelgeuse exhausts its hydrogen, it does not simply stop. It shifts. It begins fusing helium instead. When helium runs out, it shifts again to carbon, then neon, then oxygen, then silicon. Each stage produces less energy per reaction and runs faster than the one before it. The star is burning through progressively heavier fuels at progressively shorter intervals. This is confirmed nuclear astrophysics, not speculation. The sequence is well understood. What is less certain is exactly where in that sequence Betelgeuse currently sits. The outer layers have already expanded enormously, which is why the star is a red supergiant rather than the smaller, hotter star it was in its youth. That expansion happened when hydrogen burning in the core gave way to shell burning, where fusion migrates outward from the core into surrounding layers. The outer envelope puffed outward in response. The star became vast and cool at its surface, while remaining extremely hot and dense at its core. Inside that core right now, the most likely scenario, based on current modelling, is that Betelgeuse is in a late stage of helium burning or has already moved into carbon burning. A 2023 study from Japanese researchers suggested the carbon burning phase may be more advanced than earlier estimates assumed. That study used pulsation data from the star's surface as a proxy for the internal structure, essentially listening to the star's heartbeat to infer what is happening in its chest. The results were striking. The pulsation signature matched models of a star with a carbon-oxygen core consistent with advanced nuclear burning. If accurate, the remaining fusion cycles after carbon are measured in thousands of years at most, not millions. Here is the important caveat. This is a well-reasoned scientific inference, not a direct observation. We cannot see inside Betelgeuse. We read its interior the way a doctor reads a patient through indirect signals. The models are strong, but the uncertainties are real. What we do know is that Betelgeuse is not in the stable, long-burning phase of its life. It is deep into the final chapters. The interior is layered like an onion, with different elements fusing in concentric shells around a growing core of material that cannot be fused further. Each layer is hotter and denser than the one above it. When that innermost core reaches the point where no more energy can be extracted, gravity wins instantly. The collapse takes less than a second. What happens in that second, and what it sends toward Earth 650 light-years away, is one of the most violent events the universe produces, and it starts with something invisible. Before any light reaches us from a supernova, something else arrives first: neutrinos. These are subatomic particles produced in enormous quantities during the nuclear reactions happening inside stars. They are so small and so weakly interacting with normal matter that they pass through almost everything without slowing down. A beam of neutrinos could travel through a light year of solid lead, and most of them would make it out the other side untouched. When a massive star's core collapses, the density at the center briefly becomes so extreme that even neutrinos struggle to escape immediately. But within seconds, they break free, and they travel outward at nearly the speed of light, carrying with them roughly 99% of all the energy released by the collapse. This is confirmed. We know it because it already happened once in modern times. On February 23rd, 1987, a star in the Large Magellanic Cloud, a small galaxy about 160,000 light-years from Earth, went supernova. It was the closest confirmed supernova observed since the invention of the telescope. And roughly 3 hours before the visible light from the explosion reached Earth, neutrino detectors in Japan, the United States, and Russia all recorded simultaneous bursts of neutrino events, 24 neutrinos total, across 3 separate detectors in a span of 13 seconds. From a star 160,000 light-years away, that detection confirmed the theoretical model of core collapse supernovae in one of the most dramatic experimental validations in the history of physics. Today, the neutrino detectors that exist are vastly more sensitive than what was operational in 1987. The Super Kamiokande detector in Japan, buried under a mountain and filled with 50,000 tons of ultra-pure water, is specifically designed to catch neutrino bursts from nearby supernovae. At Betelgeuse's distance of 650 light-years, a core collapse would produce a neutrino signal in Super Kamiokande that scientists estimate would be detectable for hours, generating thousands of recorded events rather than 24. That signal would arrive hours before the visible explosion, possibly days, depending on how quickly the shockwave travels through the star's outer layers to the surface. In practical terms, this means that if Betelgeuse is going to explode, we will almost certainly know before we see it. The neutrino burst will trigger automated alerts at observatories worldwide. Every major telescope on Earth and in orbit would have time to point at Orion before the light show begins. That is an extraordinary thing. A dying star, 650 light-years away, sending a particle warning signal ahead of its own destruction. Traveling at nearly the speed of light through 650 years of space, arriving in a tank of water under a Japanese mountain, and triggering an alarm. What comes after the alarm is something no living human has ever witnessed from this close. And it will be visible in a way that the word spectacular does not quite cover. When Betelgeuse explodes, anyone on Earth who happens to be outside will notice. No telescope required, no special knowledge, just a clear sky and functional eyes. At peak brightness, a Betelgeuse supernova would reach an apparent magnitude of roughly -12. To put that in terms that mean something, the full moon sits at about -13. This star, which currently looks like a moderately bright reddish point in Orion, would suddenly become comparable to a second moon in the sky. The constellation Orion would be transformed. Where the right shoulder used to be, there would be a point of light, blazing so intensely it would cast shadows at night. During the day, it would be visible. Dimmer than our star, but bright enough to see as a distinct point, even with the sky fully lit. This has happened before in recorded human history. In 1054, a supernova in the Milky Way was recorded by Chinese and Arab astronomers as a new star visible in broad daylight for roughly 3 weeks. A Betelgeuse supernova would likely surpass that. The initial flash would be followed by a sustained period of extreme brightness, lasting weeks to months, as the shockwave travels through the star's ejected outer layers, heating and lighting them from within. After that peak, the brightness would begin to fade, but not quickly. A supernova remnant at this distance could remain a significant naked eye object for a year or more. Over months and then years, the remnant would expand. The material blasted outward from Betelgeuse at millions of miles per hour would form an expanding shell of hot gas and dust, glowing as it collides with the surrounding interstellar medium. Eventually, over thousands of years, that shell would grow large enough to see as an extended nebula. The Crab Nebula, the remnant of the 1054 supernova, is the nearest well-studied example of what this looks like. It is still expanding today, nearly 1,000 years later. At Betelgeuse's distance, the equivalent nebula would eventually become one of the largest and brightest objects in the visible sky, spanning a region larger than the full moon. What would be left at the center depends on exactly how massive Betelgeuse's core is at the moment of collapse. The two most likely outcomes are a neutron star, a city-sized object with the mass of several of our stars compressed into a sphere roughly 12 miles across, or a black hole if the core mass is high enough that not even the pressure of neutron matter can halt the collapse. Either outcome would sit at the center of the expanding nebula, dark, dense, spinning, and unreachable. Siwaha, if the orbital calculations are correct, would be flung outward by the sudden loss of Betelgeuse's mass, becoming a runaway star moving through the galaxy at high speed. The show would be extraordinary, and it would be completely safe to watch. 650 light-years is a number worth understanding properly. It is not just a distance, it is a delay. Every piece of light we receive from Betelgeuse left that star 650 years ago. Right now, at this moment, we are seeing Betelgeuse as it was in the 1300s. The Aztec Empire was still expanding. The Renaissance had not yet begun in Europe. The printing press did not exist. Whatever Betelgeuse is doing right now, in the actual present moment, we will not know for 650 years. This is not a trivial philosophical point. It has direct, practical significance. If Betelgeuse went supernova yesterday, in the actual present, the light from that explosion is currently traveling toward us at the speed of light and will not arrive for 649 more years. No instrument we have can detect it yet. No warning is possible until the neutrino burst arrives, which would precede the light by only hours. In other words, the explosion could already have happened. We would have no idea. Scientists are careful to say this clearly. The question of whether Betelgeuse will explode soon is really a question about what we are seeing in the data from 650 years ago. What we observe is the star as it was in the 1300s, behaving in ways consistent with being hundreds of thousands of years from collapse. But there is a look-back time baked into every measurement we take. This is not alarming in a practical sense. The star almost certainly has a very long time left, regardless of when you measure from. But it is a fundamental reminder of what observational astronomy actually is. We are not watching the universe as it is. We are watching it as it was, across a range of time delays that scales with distance. Betelgeuse is one of the closer examples of this effect. The nearest major galaxy, Andromeda, shows us its past from 2.5 million years ago. The most distant objects ever observed show us light from over 13 billion years ago, when the universe itself was less than 1 billion years old. Every time you look up at the night sky, you are looking back in time. The further you look, the deeper into the past you go. The sky is not a snapshot of the present. It is a layered record of history, with the nearest objects closest to the present and the faintest ones reaching back toward the beginning. Betelgeuse, in this sense, is the universe's way of making that abstraction personal. It is close enough to study in detail, old enough to be near its end, and dramatic enough that its changes are visible across more than a century of human observation. And understanding its distance also means understanding why the explosion, when it eventually happens, poses no threat. The confirmation on that question is more definitive than many people realize. That is where the next chapter goes. The question of whether a Betelgeuse supernova is dangerous gets asked constantly. The answer is confirmed by multiple independent lines of research. No, not even slightly. Here is the physical basis for that answer. A supernova produces several categories of potentially harmful radiation, including visible light, ultraviolet radiation, X-rays, gamma rays, and a high-energy particle flux called cosmic rays. At sufficient intensity, any of these could cause serious damage to biological systems and to the ozone layer that protects life on Earth. The threshold distance at which a supernova becomes genuinely hazardous to Earth's biosphere is estimated to be somewhere around 160 light-years. Within that range, the gamma-ray flux and cosmic ray exposure from a core collapse event could cause significant ozone depletion and elevated surface radiation levels. Some researchers have proposed that past mass extinction events in Earth's history may have been influenced by nearby supernovae, though this remains a hypothesis rather than a confirmed mechanism. Betelgeuse is roughly 4 times that distance. At 650 light-years, the energy reaching Earth from a Betelgeuse supernova, even at its peak, would be far below harmful thresholds. The visible brightness would be dramatic. The actual radiation reaching Earth's surface would be a tiny fraction of what we receive from our own star on a normal afternoon. There would be no ozone damage, no elevated cancer rates, no disruption to ecosystems, no effect on technology or communications infrastructure. The electromagnetic pulse concerns associated with nuclear weapons are driven by gamma rays at close range, not by distant stellar events of this kind. What there might be, genuinely and interestingly, is an effect on navigation for animals that use the night sky as a reference. Certain migratory birds and sea turtles use celestial cues to orient themselves. A dramatically altered night sky, with a blazing new object in Orion as bright as the moon, could create genuine confusion for species that rely on consistent star patterns or light-level baselines. Researchers have noted this as a real, if relatively minor, ecological consideration. Professional astronomers would face a different practical challenge. Ground-based optical astronomy in the direction of Orion would be effectively impossible during the peak brightness period. The supernova would saturate detectors and overwhelm fainter background objects. Observers would need to wait for the brightness to fade before resuming normal work in that region of the sky. In every other respect, life on Earth would continue as normal. Humans would have a spectacular sky event lasting months to years. A new nebula forming at the edge of Orion, visible for a lifetime or more, and a permanent addition to the history of naked-eye astronomical events witnessed by our species. It would be one of the most extraordinary things any living generation of humans has ever seen. And it would be perfectly safe to watch from a lawn chair. But knowing when to set up that lawn chair requires understanding what the last stages of Betelgeuse's life actually look like from the inside. And that sequence is far stranger and more violent than most people imagine. The final stages of a massive star's life move fast. Not fast by human standards, fast by stellar standards, which means the timescales that once measured in billions of years compress, stage by stage, into something almost frantic. Here is the sequence, as confirmed by stellar evolution models and nuclear astrophysics, starting from where Betelgeuse most likely is right now. Carbon burning, the phase many models suggest Betelgeuse may currently be in or approaching. In a star of this mass, carbon burning in the core lasts on the order of a few hundred to a few thousand years. The core temperature and density at this stage are extreme by any normal measure, but this phase still produces enough energy pressure to hold the star in equilibrium. After carbon comes neon burning. This phase lasts roughly 1 year. 1 year for a fusion process that would have taken billions of years in the hydrogen burning stage. After neon comes oxygen burning. This lasts months. After oxygen comes silicon burning. This lasts approximately 1 day. 1 day, from the start of silicon burning to the point where the silicon in the core is exhausted and converted to iron. 24 hours. And then the iron problem arrives. Iron is the end of the line for fusion energy production. Fusing lighter elements together releases energy, but fusing iron requires energy rather than releasing it. When the core fills with iron, fusion stops producing the outward pressure that holds the star up. Gravity, which has been balanced against fusion pressure for millions of years, suddenly has nothing pushing back. The collapse begins. The iron core, roughly the size of Earth at that moment, falls inward at a quarter of the speed of light. In less than half a second, it compresses to a sphere roughly 12 miles across. The density becomes so extreme that protons and electrons are forced to combine into neutrons. The core becomes a neutron star in an eye blink. The infalling outer layers of the star, crashing down toward the core at enormous velocity, hit that neutron star and bounce. The rebound sends a shockwave outward through the remaining stellar material. That shockwave, powered partly by the outpouring of neutrinos from the newly formed neutron star, tears through the outer layers of the star and explodes outward into space. This entire sequence, from the start of core collapse to the explosion reaching the surface, takes between hours and a day or two, depending on the star's exact structure. From the outside, nothing is visible until the shockwave reaches the surface. Then, suddenly, a star that was glowing at its normal level blazes to billions of times its original brightness in a matter of hours. That is what we will see, someday, where Orion's shoulder used to be. And the scale of that moment, the brightness, the duration, the permanence of what it leaves behind, is something worth describing in full detail, because no summary does it justice. Imagine waking up one morning and noticing that something is different about the sky. Even before sunrise, a glow in the east, unusual, steady, not the diffuse light of dawn, but a concentrated point, burning in the constellation Orion with an intensity that stops you mid-step. That is how the light from a Betelgeuse supernova would likely first announce itself to most people. Not with a bang, not with any sound at all, just a star, suddenly where there was not one before, blazing with a light that casts its own shadow. The hours and days following the initial eruption would be extraordinary. The brightness would climb rapidly as the shockwave expanded through the star's outer layers, heating and energizing the ejected material. Peak brightness would likely arrive within a few days to a couple of weeks after the initial detection, depending on how the explosion propagates through the star's complex structure. At peak, from a dark location away from city lights, the supernova would be the second brightest object in the night sky. It would be visible on the horizon at twilight and still glowing intensely at midnight. If you held up your hand toward it, it would cast a faint but distinct shadow. Daytime visibility is confirmed to be likely based on comparison with the historical 1054 supernova event at greater distance. Betelgeuse, being 4 times closer than that event, would be proportionally brighter. Multiple days of daytime visibility, where the star can be picked out as a distinct point against a blue sky, are considered probable by astronomers who have modelled the event. The Orion constellation would be permanently changed. Where the right shoulder of the hunter once sat, there would be this blazing intruder. Star charts would need to be updated. The familiar geometry of one of the most recognized patterns in human astronomical history would carry a new and temporary member. Over weeks and months, the brightness would fade, unevenly at first, with possible fluctuations as the expanding shockwave encountered different shells of material previously ejected by the star. Eventually, the point source would fade below naked eye visibility. But by then, the expanding nebula around it would begin to grow. In 100 years, it would be a small but detectable smudge in a backyard telescope. In 1,000 years, it might span a region of sky larger than the full moon, glowing in the characteristic colors of hot ionized gas. In 10,000 years, it would be among the largest and most spectacular nebulae visible from Earth. A permanent monument to a star that spent millions of years as the giant of Orion before going out in the most dramatic way the universe allows. Anyone alive to see the initial flash will have witnessed something with no modern precedent. The last supernova visible to the naked eye from Earth was in 1987, and it was 10 times farther away than Betelgeuse and far less bright. What Betelgeuse will produce when it goes is in a different category entirely. And the question of when, while still uncertain, is no longer the simple unknown it was before Siwaha was discovered. Before Siwaha was confirmed, the timeline question was genuinely open in a worrying direction. The data from Betelgeuse itself, the unusual brightness swings, the deep dimming event, the pulsation data suggesting advanced nuclear burning, all of it pointed toward a star that might be closer to the end than the standard models suggested. Researchers were careful in their public statements, but the data was not comfortable. The 2023 Japanese study that analyzed pulsation signatures suggested a supernova timeline that could be measured in tens of thousands of years rather than hundreds of thousands. Some interpretations of that data reached even shorter estimates, though those were at the more speculative end of the range. Then Siwaha was confirmed, and the reanalysis began. Here is what changed. A significant portion of Betelgeuse's unusual behavior, specifically the 6-year brightness cycle and the spectroscopic variations tied to it, was now attributable to the orbital influence of the companion. That meant the data previously being interpreted as evidence of internal stellar instability was at least partly, and perhaps largely, an external signal. The alarming brightness swings that seemed to suggest a star in accelerating distress were partially an orbital artifact. Remove Siwaha's contribution from the data, and the underlying behavior of Betelgeuse itself becomes somewhat more consistent with a star that still has time. The current best supported estimate, accounting for the binary system context, places the supernova somewhere between 100,000 and a few 100,000 years in the future. Some models lean toward the shorter end of that range, some toward the longer. The honest answer is that the uncertainty is real, and the precision of these estimates is limited by what we can observe from 650 light-years away. What the Siwaha discovery did not do is eliminate the uncertainty. It redirected it. The question is no longer just about Betelgeuse's internal evolution. It is also about how the binary interaction affects that evolution over time. A companion star orbiting inside the outer atmosphere of a red supergiant is not a passive observer. Siwarha is shedding angular momentum into the surrounding gas. It is affecting the mass loss rate of Betelgeuse by stirring material that might otherwise remain bound to the star. It may be influencing the rate at which Betelgeuse sheds its outer envelope, which in turn affects how quickly the core evolves. These interactions are not fully modelled yet. This is an active area of research. The 2027 observing window, when Siwaha re-emerges from behind Betelgeuse, will provide data that feeds directly into refining these models. The universe has a way of making its most interesting puzzles the hardest to fully solve. Betelgeuse, up close and observable and strange, is one of the richest puzzles in the current sky, and understanding it has value that extends far beyond one star in one constellation. Because what Betelgeuse is teaching us applies to stars, we will never be able to study this closely. Most red supergiants in the galaxy are invisible to us as individuals, not because they do not exist. They do, by the thousands. But they are distant, small in apparent size, buried in stellar crowding, or simply too faint to observe in detail. We see their light as part of the aggregate glow of the Milky Way. We cannot map their surfaces, track their companions, or measure their atmospheric dynamics. Betelgeuse is the exception. Close enough to resolve directly, bright enough to study across every wavelength, active enough to show us behaviors we can actually follow in real time. That makes everything we learn from it a template, a reference point, a key for reading the behavior of stars we cannot see as clearly. Red supergiants are the immediate predecessors of core collapse supernovae. Every Type II supernova in the universe, the kind produced by massive star collapse, begins with a red supergiant or a closely related class of star. Understanding how these objects lose mass, interact with companions, vary in brightness, and evolve through their final stages is not just an academic exercise. It is foundational to understanding how the universe recycles material from dying stars into new ones. Here is a fact that puts this in perspective. Every atom of iron in your blood was forged in the core of a massive star that lived and died billions of years ago. Every atom of calcium in your bones, every atom of oxygen in the air. The heavy elements that make up the physical structure of life on Earth did not exist when the universe began. They were built inside stars and scattered into space when those stars exploded. Betelgeuse is a factory for future material. Right now, its stellar winds and mass ejection events are seeding the surrounding space with the raw ingredients of future planetary systems. When it eventually explodes, it will add to that inventory dramatically, scattering newly synthesized heavy elements across a sphere of space hundreds of light years wide. Siwaha's role in this process is now understood to be real and significant. By stirring the outer atmosphere and contributing to the mass loss rate, it is influencing how much material Betelgeuse releases before the final explosion. Binary interactions in massive star systems are now recognized as a major factor in stellar evolution, and Betelgeuse and Siwaha are one of the closest and most detailed examples of this process we have ever observed. The 2027 observation window will sharpen what we know about the current state of both stars. The measurements that come out of that period will feed into models that apply to thousands of similar systems too far away to study directly. In this sense, Betelgeuse is more than a local curiosity. It is a window into how the galaxy works at a fundamental level. A star we have watched with naked eyes for thousands of years is now teaching us something about the deep mechanics of stellar life and death that we could not have learned any other way. There is one last thing worth saying about what all of this means for us. Not as astronomers, as people looking up. Humans have been watching Betelgeuse for a very long time, long before the name was written down, long before anyone understood what a star was. The reddish glow at the shoulder of the hunter figure in Orion has been part of the human night sky experience for as long as people have looked up and tried to make sense of what they saw. Ancient Mesopotamian astronomers tracked it. Arab scholars named it and incorporated it into their celestial maps. Indigenous astronomical traditions across multiple continents identified the star and assigned it meaning within their understanding of the sky. Medieval European navigators used it as a reference point. The name we use today in English is a corruption of an Arabic phrase meaning the hand of the giant, arrived at through a long chain of translation, transcription, and eventual error in typesetting centuries ago. For all of that time, the star was simply there, consistent, familiar, part of the permanent architecture of the sky. What the past decade of observations has done is reveal that the star is not what it appeared to be. It is not a single, isolated, slowly dimming giant waiting quietly to explode. It is a binary system, a dynamic, interacting pair of stars, one enormous and old, and throwing off material in every direction, one smaller and younger, and cutting through the atmosphere of its companion with every orbit. It is louder, messier, and more complicated than the still point of reddish light suggested, and, in a way, that complication makes it more interesting. A system with a hidden companion star, a gas wake visible across light years, a surface covered in planet-sized convection cells, a history of dramatic dust ejections, and a future that ends in one of the most violent events the universe produces. All of it happening a cosmic stone's throw away. The data coming from Betelgeuse is still being analysed. The 2027 observation window will add to it significantly. Future instruments, including next-generation space telescopes and ground-based observatories currently under construction, will bring new capability to bear on the system in the coming decade. Every observation refines the picture. Every refinement raises new questions. That is the nature of science, and Betelgeuse has proven to be one of the most reliably surprising subjects in the modern era of stellar astronomy. Whoever is alive when this star finally goes will witness something that no human being has ever seen from this planet. A nearby supernova. A new object in the sky brighter than anything except the body that lights our days. A permanent change to the constellation that has guided human navigation, myth, and wonder for longer than written history extends. For now, it is still there, still glowing, still changing, still watched. A star in the shoulder of Orion, 650 years in our past, burning through the last chapters of a life measured in millions of years, with a companion nobody knew existed until last year, cutting a wake through its outer atmosphere every 6 years. The sky is never as simple as it looks, and Betelgeuse is the best reminder of that we have. What the discovery of Siwaha tells us goes beyond one star system. Before this detection, the assumption in much of stellar astronomy was that isolated stars, or stars with distant, wide companions, were the norm for massive red supergiants. Binary systems involving a close companion were acknowledged as possible, but rarely confirmed at this stage of stellar evolution. The technical challenge of finding a faint companion in the glare of a supergiant was simply too great for most instruments. Alopec cracked that barrier. The speckle imaging technique, combined with the Gemini North Telescope's elevation and mirror size, provided the combination of contrast and resolution needed to pull a point of light from inside the blazing halo of Betelgeuse. Now, astronomers are revisiting assumptions about other red supergiants with unexplained long secondary periods. If Betelgeuse has a companion responsible for its 6-year cycle, it is reasonable to ask whether other variable red supergiants with similar unexplained periods might also have hidden companions. Several candidates are already identified in the literature. This is not confirmed yet. It is a productive scientific hypothesis prompted by the Betelgeuse discovery, but if it holds up across other systems, it would revise significantly upward the estimated frequency of close binary interactions in massive stars, and that has consequences for how we model supernova rates, stellar mass loss, and heavy element production across the galaxy. There is also the question of what happens to Siwaha specifically when Betelgeuse explodes. Models of binary supernovae show a range of outcomes depending on the masses involved and the separation at the time of collapse. In some scenarios, the surviving companion is ejected as a runaway star, possibly carrying chemical enrichment from absorbed material it picked up during its long orbit inside Betelgeuse's atmosphere. In others, if the mass loss during the explosion is dramatic enough, Siwaha could end up bound to the resulting neutron star or black hole, forming a new kind of system entirely. These outcomes are all theoretical at the moment. None can be confirmed without the event itself happening. But the models are specific enough that when a Betelgeuse supernova does eventually occur, astronomers will be looking for Siwaha afterward, trying to determine which scenario played out. The star system that looked like a simple solitary giant turns out to be a layered, interacting, evolving pair of objects, each shaping the other's behavior and eventual fate. That kind of complexity, hidden behind a point of light visible to anyone who steps outside on a clear winter night, is exactly what makes observational astronomy so persistently surprising. The universe hides enormous things in plain sight. It hid Siwaha in the glare of one of the most observed stars in human history for as long as we have had telescopes. What else might be hiding in plain sight among the stars we think we know? That question does not have an answer yet, but the tools being built right now are specifically designed to find out. The next generation of telescopes is already being built with stars like Betelgeuse in mind. The extremely large telescope, currently under construction in Chile, will have a primary mirror roughly 130 feet across when completed. That is larger than most residential houses. It will be the largest optical telescope ever built, and among its primary science goals is the study of stellar surfaces and nearby stellar systems in detail that current instruments cannot achieve. At Betelgeuse's distance, the extremely large telescope will be capable of resolving surface features smaller than anything currently imageable. Individual convection cells, dynamic brightness, asymmetries, and potentially the spatial track of Siwaha's influence on the surrounding atmosphere could all be mapped with a resolution that would have been unthinkable a decade ago. The Nancy Grace Roman Space Telescope, a wide-field infrared observatory scheduled for launch in the coming years, will provide new capability for tracking the circumstellar environment around Betelgeuse at infrared wavelengths. The expanding and complex shell of material surrounding the star, built up over millions of years of mass loss and now being stirred by Siwaha's orbit, could be mapped in unprecedented detail. Ground-based interferometric arrays, including upgrades to the Very Large Telescope interferometer and new facilities planned for the coming decade, will continue to image the stellar disk directly, tracking surface changes across years and potentially resolving the influence of Siwaha's passage on the star's visible hemisphere. The 2027 observing window is the nearest term milestone in all of this. When Siwaha moves back into a position directly observable from Earth, the combination of instruments available will be significantly more capable than what was in operation when the companion was first detected in 2024. Researchers will be watching the companion's re-emergence with every tool currently at their disposal. What they are hoping to measure includes the temperature and luminosity of Siwaha directly, the structure of the gas wake immediately behind it, any evidence of material transfer between the two stars, and whether Siwaha's own spectrum shows signs of chemical enrichment from years of orbiting inside Betelgeuse's outer layers. Each of those measurements will feed into models of binary stellar evolution that currently rely more on theory than on direct observation. Betelgeuse sits at the intersection of nearly every major question in massive star astrophysics. How do giant stars lose mass? How do binary interactions affect stellar evolution? What are the precursor signatures of a core collapse supernova? How do heavy elements move from dying stars into the surrounding interstellar medium? One star, 650 light-years away, with a companion nobody knew existed until last year, providing answers, or at least better questions, about all of it. The instruments are being built, the observations are being planned, and the star is still there, still changing, still waiting to be understood more fully than it is today. The final chapter of this video is not about instruments or timelines. It is about what Betelgeuse means when you step back all the way and look at the full picture. Step back far enough from any star and it becomes a point of light. No surface detail, no companion, no convection cells or gas wakes or brightness cycles, just a dot in the dark. The universe is full of these dots, hundreds of billions in our galaxy alone. Each one a system with its own complexity, its own history, its own eventual end. We cannot study most of them. The distances are too great, the instruments too limited, the lifetimes of observations too short relative to the timescales on which stars change. Most of what happens in stellar life and death is inferred from models, built from theory, or extrapolated from the behavior of statistical populations. Betelgeuse is different. It is close enough to be a laboratory, a place where we can watch stellar physics operating in real time, where the surface can be mapped, the companion detected, the wake measured, the spectral shifts tracked across years, where the abstractions of stellar evolution theory become concrete, observable, specific. And what Betelgeuse is showing us, after years of strange behavior and careful study, is that reality is more complicated than the models assumed. A companion nobody suspected for most of modern astronomy's history, a gas wake that explains a mystery 6 years in the making, a mass ejection so large it briefly dimmed the star to a historic low, a surface covered in convection cells the size of planetary orbits, an interior burning through the final stages of nuclear fusion on timescales that compress from billions of years down to hours. All of it happening in a star we have watched since before we understood what stars were. There is something worth holding on to in that. Not alarm, not dread. The supernova is not imminent. Earth is not in danger. The timeline, even at the short end of current estimates, is measured in timescales that dwarf all of recorded human civilization. What it is worth holding on to is the recognition that the sky we look at is not static. It is not a backdrop. It is a place where things happen, where matter transforms, where systems evolve, where the processes that created the atoms in our bodies are still running, still producing, still scattering the ingredients of future worlds into the dark. Betelgeuse is doing all of that right now. From 650 light-years away, it is losing mass, stirring its companion's orbital path, building a circumstellar envelope, and slowly, inexorably, approaching the end of a stellar life that began 10 million years ago. When it finally explodes, it will be visible to the naked eye from Earth. It will change the appearance of Orion for a human lifetime. It will scatter freshly forged atoms into the surrounding space, contributing to the raw material of whatever comes next in that region of the galaxy. And somewhere, if the models are right, Siwaha will be flung outward, a lone star moving through the Milky Way at high speed, carrying with it the chemical memory of the giant it once orbited. The sky is never as simple as it looks. Betelgeuse has been proving that for as long as anyone has looked up. Everything we have covered in this video points toward a single conclusion. Betelgeuse is not dying faster than expected. It is not a threat to Earth. It is not on the verge of an explosion that will reshape our world. The confirmed science, as of the most recent observations, paints a picture of a complex, fascinating, deeply strange stellar system that still has a very long time left. But it is also genuinely and verifiably one of the most extraordinary objects in the modern sky. A red supergiant so large it would swallow the inner planets, a binary companion that hid inside its glare for the entire history of telescopic astronomy and was only detected in late 2024. A gas wake confirmed by the Hubble Space Telescope that explains a 6-year mystery stretching back through decades of observations. A surface covered in planet-sized boiling columns of gas. An interior working its way through the final fuel cycles of stellar evolution. A surrounding shell of ejected material that will eventually become one of the most spectacular nebulae in our sky. And underneath all of it, the deep time frame of stellar physics, a star that has been burning for 10 million years, an explosion that may still be hundreds of thousands of years away, a future nebula that will expand and glow for tens of thousands of years after that. This is what the universe does. It operates on scales that make human timelines look like rounding errors. It builds structures over millions of years and tears them apart in seconds. It hides companions in plain sight and leaves wakes visible from 650 light-years away. Betelgeuse is close enough that we get to watch this process in detail, close enough that the surface can be resolved, the companion detected, the wake measured, and the brightness cycles tracked across generations of observation. In a galaxy of hundreds of billions of stars, most of which we will never be able to study this closely, that proximity is genuinely rare. The story of Betelgeuse is still being written. The 2027 observing window will add new data. The next generation of telescopes will add more. Every year of monitoring refines the picture, raises new questions, and occasionally produces the kind of surprise that Siwaha's detection represented. Science does not promise certainty. It promises a method, a way of looking at the sky that takes the data seriously, follows the evidence, revises the models when new information arrives, and builds understanding that accumulates over time. The universe is stranger than the models assumed. It usually is. Betelgeuse reminded us of that. A reddish point of light in the shoulder of Orion, watched by humans for thousands of years, still finding new ways to surprise the people looking up at it. That is not alarming. That is extraordinary. And the sky is full of it.